April 26, 1942. Lieutenant Commander Edward Henry Butch O'Hare walked into the Grumman Aircraft Engineering Corporation facility in Bethpage, New York, carrying a briefcase full of combat reports that would change the course of the Pacific War. 4 days earlier, he'd been touring factories as part of a Navy morale campaign, fresh from his Medal of Honor citation for single-handedly defending the carrier Lexington against 9 Japanese bombers. But today wasn't about parades or publicity. Today was about survival. Leroy Grumman, the company's founder, was waiting for him in the engineering office, along with chief designers Leon Jake, Swirbul and Bill Schwendler. On the drafting tables behind them sat blueprints for the XF-6F1, Grumman's proposed replacement for the F4F Wildcat that O'Hare had been flying in combat. The prototype was scheduled for its first flight in exactly 2 months. Production contracts had already been signed. Everything was on schedule. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Everything except the airplane itself, which O'Hare was about to tell them, was fundamentally wrong. O'Hare laid his combat reports on the table. Action over Rabaul, engagement near the Coral Sea, the recent slaughter at the Battle of Midway, where American pilots had discovered what every combat aviator in the Pacific already knew, but headquarters hadn't wanted to hear. The Japanese Mitsubishi A6M0 was faster than the Wildcat. It climbed better than the Wildcat. It turned inside anything the Americans could put in the air. And pilots were dying because of it. Grumman looked at the reports, then at the blueprints for the XF-6F1. The prototype sitting in the hangar outside was powered by a Wright R2600 Cyclone engine, 1600 horsepower, the same engine Grumman was using for their new TBF Avenger torpedo bomber. It was reliable, it was available, and it was already integrated into the design. Switching engines now would mean redesigning the entire airframe, strengthening the structure, modifying the cowling, changing the propeller. It would delay production by months, but O'Hare wasn't asking for a better airplane. He was explaining why the current design would get pilots killed. The Bureau of Aeronautics hadn't waited for O'Hare's visit to reach the same conclusion. Combat reports from Coral Sea and Midway had been flooding in for weeks. American fighters weren't just being outperformed, they were being systematically destroyed by an enemy aircraft that had been designed to a completely different set of priorities. The Zero sacrificed armor and firepower for maneuverability and range. The Wildcat was tough and well-armed but couldn't catch a Zero, couldn't climb with a Zero, and couldn't run away from a Zero. Pilots were winning through tactics and courage, not through superior equipment. On that same day, April 26, 1942, the Bureau of Aeronautics sent a directive to Grumman that would become one of the most consequential decisions in naval aviation history. Abandon the Wright R2600 engine. Install the Pratt & Whitney R2000 800 double wasp instead. 18 cylinders, 2,000 horsepower. The same engine powering the Vought F4U Corsair and the Republic P-47 Thunderbolt, the most powerful production radial engine in the world. Grumman's response to this directive would determine whether the Navy got a marginally improved Wildcat or a fighter that could dominate the Pacific. Because changing engines wasn't a simple swap. The R2800 weighed 300 pounds more than the R2600. It was physically larger. It produced 25% more power, which meant 25% more stress on the airframe, the engine mounts, the propeller system. Everything would have to be redesigned and strengthened, and they had less than 2 months to figure it out before the prototype was supposed to fly. Bill Schwendler, Grumman's chief designer, looked at the specifications for the R2800 and realized something that should have been obvious but had been obscured by engineering conservatism. The XF-6F1 as designed was too heavy and too underpowered for what the Navy actually needed. Schwendler had suspected this during the initial design work. He'd even suggested the R2800 originally, back in mid-1941 when the contract was signed. But the Navy had insisted on the R2600 because it was available, because supply chains were established, because Pratt & Whitney couldn't promise enough R2800 seconds to go around with the Corsair and Thunderbolt also in production. But that was before Pearl Harbor. That was before American pilots started dying in numbers that made procurement logistics look like a trivial concern. Leroy Grumman made a decision that probably violated a dozen procurement regulations. He went around official channels and called in personal favors with Pratt & Whitney executives to secure delivery of R-2800 engines. He convinced the Navy that delays now would save lives later, and he put his entire design team on a crash program to redesign the F4F airframe to handle the more powerful engine. They had weeks, not months. The prototype was already partially assembled. Changing horses midstream like this was the kind of thing that sank companies and ended careers. But Grumman had built his reputation on one simple principle: build what works, not what looks good on paper. If the paper said the R-2600 was adequate and the combat reports said it wasn't, you believed the combat reports. The original XF6F1 prototype made its first flight on June 26, 1942, with the Wright R-2600 engine installed, piloted by Grumman test pilot Bob Hall. The flight was essentially a formality, a checkbox to satisfy the original contract requirements. Grumman and the Navy both knew that this version of the aircraft was already obsolete before it left the ground. The real work was happening on the second prototype, which was being completely reworked to accommodate the R-2800. The redesign required more than just a bigger engine mount. The entire forward fuselage had to be strengthened to handle the additional power. The engine cowling needed to be enlarged and reshaped. The propeller had to be changed from a Curtiss Electric to a Hamilton Standard 3-blade unit that could absorb the 2,000 horsepower without tearing itself apart. The landing gear, already strengthened compared to the Wildcat, needed further reinforcement because the aircraft was going to be heavier and faster. But the most critical change was less obvious. The additional power meant the F6F could carry more weight without sacrificing performance. More armor, more ammunition, more fuel. The original XF6F1 design had tried to keep weight down to maximize performance with the underpowered R-2600. The XF6F3, the redesignated second prototype with the R-2800, could afford to be heavier because it had the power to move that weight at combat speeds. This meant Grumman could give Navy pilots what they'd been begging for since the first encounters with Zeros: protection. The F6F3 design incorporated 212 pounds of cockpit armor, plates behind the pilot's seat, plates protecting the oil tank and oil cooler, bulletproof glass in the windscreen. The massive R-2800 engine itself served as additional armor, a wall of steel between the pilot and any head-on attack. Self-sealing fuel tanks, a feature the Zero lacked, were built into the fuselage to prevent catastrophic fires from battle damage. The Japanese had designed the Zero around a philosophy that said speed and maneuverability were worth sacrificing survivability. American pilots would win by being better, faster, more skilled. The F6F was being designed around a different philosophy. Young pilots with 200 hours of flight time were going to have to fight veteran Japanese aviators with thousands of hours of combat experience. The airplane had to compensate for that gap. It had to keep them alive long enough to learn. It had to be forgiving, stable, tough enough to take damage and still get the pilot home. On July 30th, 1942, exactly 1 month after the first prototype flew, Bob Hall took the XF6F3 up for its maiden flight. The aircraft with the R-2800 engine. The performance increase was exactly what Grumman had predicted: 25% improvement across the board. Maximum speed jumped from 360 miles per hour to 380. Rate of climb increased from 2,800 feet per minute to over 3,400. But the numbers told only part of the story. The XF6F3 felt different. It had power in reserve. A pilot could pull into a high-speed climb, and the engine would keep pulling. You could dive away from trouble and accelerate through speeds where the Zero's controls stiffened up. The aircraft was heavier than the Wildcat by over 1,000 pounds fully loaded, but it flew like a lighter plane because it had the power to move that mass. Test pilots reported that the F4F was viceless. No unusual handling characteristics. No nasty surprises at high speed or low speed. It was stable enough for a rookie to land on a carrier deck, but responsive enough for combat maneuvering. The Navy had ordered production of the F6F3 back in May, before either prototype had flown. That was how desperate the situation had become. They couldn't afford to wait for test results. They needed fighters that could beat the Zero, and they needed them in numbers that would overwhelm whatever the Japanese could put in the air. Grumman was already constructing Plant No. 3 in Bethpage, specifically to produce the Hellcat, obtaining structural steel by purchasing scrap from the demolished 2nd Avenue Elevated Railway in Manhattan because wartime priorities made new steel almost impossible to procure. The first production F6F3 rolled off the assembly line on October 3, 1942. 5 months after the engine swap decision, 16 months from initial design to production aircraft. The kind of development speed that would be considered impossible in peacetime procurement. But this wasn't peacetime. This was a war where American carrier pilots were flying aircraft they knew were inferior to what the enemy had, and they were flying those missions anyway because there was no alternative. By February 1943, Fighting Squadron 9 aboard the USS Essex took delivery of the first operational Hellcats. The pilots who transitioned from Wildcats to Hellcats reported the change felt like going from a pickup truck to a racing car. Everything was bigger, faster, heavier, but also smoother and more responsive. The cockpit sat higher in the fuselage, giving better visibility. The forward fuselage sloped down slightly to the engine cowling, another design refinement that came from O'Hare's combat feedback, maximizing the pilot's view forward and down, critical for spotting enemy aircraft below. The Hellcat's armament was straightforward and devastating. 6 Browning .50 caliber machine guns mounted in the wings, 3 per side, with 400 rounds per gun. That was 2,400 rounds total, nearly twice the ammunition capacity of a standard Wildcat. The guns were positioned outboard of the wing fold line, which meant they could be serviced and loaded without folding the wings, speeding up turnaround time on carrier decks. Each gun fired at roughly 800 rounds per minute. That meant a pilot could hold the trigger down for roughly 30 seconds of continuous fire before running dry. In practice, pilots learned to fire in short bursts, 2 seconds, 3 seconds maximum. That was enough to deliver 60 to 70 rounds from all 6 guns, 12 pounds of lead and steel converging on a target. Against the unarmoured fuel tanks and light structure of a Zero, that kind of firepower was catastrophic. A Hellcat pilot didn't need to be a perfect marksman. He just needed to get close enough that a short burst would intersect the target. The 6-gun spread pattern was forgiving of minor aim errors, another design feature meant to help young pilots score kills against veteran opponents. The first combat mission for the Hellcat came on August 31st. 1943. Marcus Island, a Japanese base roughly 700 miles southeast of Tokyo. Fighting Squadrons 5, 6, and 9 launched from USS Yorktown, USS Independence, and USS Essex, 24 Hellcats total, escorting dive bombers and torpedo planes against Japanese installations. Japanese fighters rose to intercept, the first real test of whether Grumman's gamble on the R2800 engine had paid off. Lieutenant Commander Charles Crommelin, leading VF5, reported the engagement in his after-action report with typical aviator understatement. The F6F is superior to the Zero, in all respects except low-speed maneuverability. What he meant was that the Hellcat could outrun it, outclimb it, outdive it, and shoot it down before the Zero's superior turning ability mattered. American pilots had learned hard lessons over the previous 18 months. Don't try to dogfight a Zero in a turning engagement. Use speed and altitude. Make high-speed passes, fire on the run, climb back to altitude using superior power and climb rate, then repeat. The Zero couldn't follow a Hellcat into a high-speed dive because its controls locked up over 220 knots. It couldn't chase a Hellcat in a climb because it simply didn't have the power. And it couldn't run away because the Hellcat was faster in level flight. The Marcus Island raid destroyed 8 Japanese bombers on the ground and shot down several fighters for the loss of 2 Hellcats to anti-aircraft fire. More importantly, it validated the tactics and confirmed that the F-6F could do what it had been designed to do: survive in combat and kill enemy aircraft. The real proof came in December 1943 during an engagement near Kwajalein. 91 Hellcats encountered roughly 50 Japanese aircraft, half of them Zeros. The ensuing air battle lasted less than 15 minutes. When it was over, 28 Japanese aircraft had been shot down. The Hellcats lost 2. The kill ratio was exactly what the Navy needed, not because American pilots were suddenly better trained, though training was improving, but because they were finally flying an aircraft that could exploit the Zero's weaknesses while compensating for the Hellcats' own limitations. The engine swap that Grumman and the Navy had rushed through in spring 1942 hadn't just made the Hellcat faster, it had made it survivable. The extra power meant pilots could carry the weight of armor and self-sealing fuel tanks without sacrificing performance. It meant they could climb away from trouble instead of being forced to dive away and hope. It meant they had enough reserve power to control the aircraft, even with battle damage that would have made a less powerful fighter unflyable. Hellcats came back to carriers with holes in the fuselage, damaged control surfaces, cylinders shot out of the engine, and they still landed safely because the R-2800 had power to spare. By mid-1944, the Hellcat had become the standard carrier fighter for the U.S. Navy. The F4U Corsair, with its higher top speed and better climb rate, was still struggling with carrier landing problems and had been transferred to the Marine Corps for land-based operations. The Corsair was the better pure fighter, but the Hellcat was the better carrier fighter because it was easier to land, more stable, and more forgiving of pilot error. In a naval war where every carrier landing was a controlled crash, those qualities mattered more than an extra 20 miles per hour in top speed. The Great Marianas Turkey Shoot, on June 19th and 20th, 1944, demonstrated what happened when you gave competent pilots superior equipment and put them up against an enemy whose experienced aviators had been systematically killed off over 2 years of attrition warfare. The Japanese mobile fleet launched wave after wave of aircraft against the American carrier task force. Hellcats from 15 carriers rose to meet them. The Japanese lost over 300 aircraft in 2 days. American losses were minimal, not because American pilots were supermen, but because the Hellcat gave them every possible advantage: speed to intercept incoming raids, firepower to destroy targets with short bursts, armor to survive hits from defensive gunners, and enough fuel capacity to loiter on combat air patrol for hours waiting for threats to appear. Grumman had estimated in July 1942 that the R-2800 engine would increase the XF-6F3's performance by 25% over the original R-2600 design. That prediction turned out to be conservative. The real improvement wasn't measured in percentages. It was measured in kill ratios. 19 Japanese aircraft destroyed for every Hellcat lost in air-to-air combat. 5,156 Japanese aircraft shot down by Hellcats over the course of the war. 75% of all U.S. Navy aerial victories. 305 Hellcat pilots became aces, scoring 5 or more kills. The Navy's all-time leading ace, Commander David McCampbell, scored all 34 of his victories flying the Hellcat. But the numbers only tell part of the story. The real measure of the Hellcat's success was that pilots trusted it. They knew it would bring them home. They knew it could take damage and keep flying. They knew that in a fight with a Zero, if they followed their training and exploited the Hellcat's advantages, they would win. That confidence, built on the foundation of Grumman's engineering and the R-2800's brutal reliability, changed the psychological balance of the Pacific Air War. The F6F5, introduced in mid-1944, incorporated refinements and upgrades learned from combat experience: a more streamlined cowling, an improved windshield, spring tabs on the ailerons for better maneuverability, the R-2800 10 watts engine with water injection, capable of 2,200 horsepower for short bursts in combat. If you find this story engaging, Please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Provision for carrying bombs and rockets, transforming the Hellcat from a pure fighter into a multi-role attack aircraft. 6,436 F6 F5 seconds were produced, more than any other Hellcat variant, because by late 1944, the Navy had figured out the formula and was mass-producing it. The production numbers revealed the scale of American industrial power once it was fully mobilized. Grumman built over 12,200 Hellcats between October 1942 and November 1945, 12,000 aircraft in 3 years. At peak production in mid-1944, Grumman was completing over 500 Hellcats per month, more than one aircraft every 90 minutes, 24 hours a day, 7 days a week. The workforce at Plant No. 3 grew to over 20,000 employees, most of them women, most of them with no prior experience in aircraft manufacturing. They were building fighters on assembly lines while the buildings were still being constructed around them. The Hellcat's design philosophy, the decision to prioritize reliability and ease of production over cutting-edge performance, meant that modifications during production were minimal. The F6 F3 that entered service in August 1943 was fundamentally the same aircraft as the F6 F5 that ended the war in August 1945. No major redesigns, no production delays to incorporate experimental features, just steady, relentless manufacturing of a design that worked. Grumman advertised that the Hellcat had been designed to be flown by 200-hour farm boys, and that wasn't marketing hyperbole, it was engineering philosophy. Make it simple enough that minimally trained pilots can fly it safely, tough enough that combat damage won't kill them, and powerful enough that they can win even if they're not the most skilled pilot in the fight. The Royal Navy received over 1,200 Hellcats under Lend-Lease, initially calling them Gannets before standardizing on the American name. British pilots praised the aircraft's docile handling characteristics and operational reliability. Fleet Air Arm Hellcats operated in the Mediterranean, off Norway, and eventually in the Pacific as part of the British Pacific Fleet. They never faced the concentrated opposition that US Navy pilots encountered, but they confirmed that the Hellcat performed as advertised in the hands of pilots from different training backgrounds and tactical traditions. The mythology around the Akutan Zero, the intact A6M2 captured in the Aleutians in June 1942, has overshadowed the real story for decades. The myth says American engineers studied the captured Zero and rushed the Hellcat into production to counter it. The chronology proves that's impossible. The XF6F1 flew on June 26, 1942, the same month the Zero crashed. The Akutan Zero wasn't recovered and shipped to California until August. Flight testing didn't begin until September, and the first production F6F3 flew in October, just 2 weeks after the Zero test started. There wasn't time to influence the Hellcat's design. What the Akutan Zero did provide was detailed intelligence on the Zero's handling characteristics and weaknesses. Test pilots at Naval Air Station Patuxent River flew mock dogfights between the captured Zero and American fighters, including the Hellcat, documenting exactly how the Japanese aircraft performed at different speeds and altitudes. That information was disseminated to fleet squadrons as tactical doctrine. Don't dogfight the Zero. Use speed, power. Avoid slow-speed turning engagements where the Zero's lightweight and large wing area gave it an advantage. The Thach Weave, the defensive scissors maneuver that Jimmy Thach had developed before the Akutan Zero was ever captured, became standard doctrine. Pilots learned to fight as pairs and sections, covering each other, never getting isolated in one-on-one turning fights. The Hellcat didn't win because American engineers copied the Zero's secrets. It won because Grumman and the Navy made the correct fundamental decisions in April 1942. Choose the more powerful engine, even though it complicated everything. Prioritize pilot protection, even though it added weight. Design for ease of production and maintenance, even if it meant sacrificing the absolute maximum performance. Build an airplane that young, minimally experienced pilots could fly safely and use effectively in combat. Those decisions, made under time pressure with incomplete information, created the fighter that dominated the Pacific for the last 2 years of the war. Bill Schwendler, the designer who'd advocated for the R2800 from the beginning, never received public recognition during the war. Neither did Jake Swirbul, who solved the production challenges that turned a prototype into 12,000 operational aircraft. Leroy Grumman's name stayed on the company, but the individual contributions of the engineering team remained classified or simply unrecorded. The pilots who flew the Hellcats became aces and heroes. The aircraft itself became legendary. But the decision-makers who'd pushed through the engine change in spring 1942, who'd taken the risk of delaying the program to get it right, largely disappeared from the historical record. The lesson that emerged from the Hellcats' development was both simple and profound. Sometimes the difference between winning and losing isn't about having the most advanced technology, it's about making the right engineering, trade-offs for the actual conditions you'll face. The Corsair was faster than the Hellcat. The Zero was more maneuverable than the Hellcat. But the Hellcat combined speed, firepower, protection, reliability, and ease of operation in a package that was optimized for carrier warfare in the Pacific. It was the right airplane at the right time, built by people who understood that perfect is the enemy of good enough, and good enough delivered in quantity beats perfect delivered late. Lieutenant Commander Butch O'Hare, whose combat feedback had helped convince Grumman to redesign the F6F around the R2800, didn't live to see the Hellcat's full impact. He was killed in action on November 26, 1943, flying a night mission over the Gilbert Islands. He was flying an F6, F3, still an early production model without the upgrades that would come later. But even that early Hellcat represented the transformation that his April 1942 visit to Grumman had helped catalyze. The Navy named Chicago's O'Hare International Airport after him. What they couldn't put on a memorial plaque was that his contribution to the Hellcat's development probably saved more American lives than any other single action in his brief combat career. The F-6F Hellcat remained in frontline service until the end of the war. By 1945, when Japan surrendered, the Hellcat had comprehensively proven that the April 1942 engine decision had been correct. The R2800 had given the F-6F exactly the edge it needed. Not overwhelming superiority in any single performance category, but enough of an advantage in the metrics that actually mattered in combat, that trained pilots could exploit those advantages consistently. Speed to control engagement geometry, power to maintain energy in climbs and dives, firepower to destroy targets quickly, protection to survive mistakes and battle damage, and reliability that meant the aircraft would be available when needed, mission after mission, day after day. After the war, Hellcats were rapidly phased out of frontline service as jet aircraft and more advanced piston fighters became available. But F-6, F-5 Newton's night fighters with radar remained in service until 1954, almost a decade after the last production aircraft rolled off the assembly line. The basic design was sound enough that even as technology advanced, the Hellcat could still perform useful missions. Some were converted to F-6, F-5 Kelvin's target drones and used in atomic bomb tests at Bikini Atoll. Others were transferred to foreign air forces under military assistance programs. The last operational Hellcats flew in South American air forces into the 1960s, more than 20 years after that April day when the Bureau of Aeronautics told Grumman to change engines. The engineering decision that transformed the F-6F from an adequate fighter into a war-winning design wasn't dramatic. There was no eureka moment, no brilliant lone inventor, no secret captured enemy technology. There was just a bureaucrat at the Bureau of Aeronautics who looked at combat reports and realized the R2600 engine wasn't good enough. There was a pilot who'd fought Zeros and knew what performance characteristics actually mattered. And there was an aircraft company willing to accept delays and complications to build what the war required, rather than what the contract specified. The story that gets told about the Hellcat is that it destroyed over 5,000 Japanese aircraft and achieved a 19-to-1 kill ratio. Those numbers are impressive, but they're the outcome, not the explanation. The real story is that in April 1942, with the Navy still reeling from Pearl Harbor and desperate for equipment that could win, someone made the decision to delay production and install a better engine. That decision required convincing executives, engineers, and procurement officials that short-term pain was worth long-term gain. It required Leroy Grumman to use personal relationships and political capital to secure R2800 engines that were supposed to go to other programs. It required Bill Schwendler and his design team to work around the clock, redesigning an airframe to handle more power and more weight. And it required the Navy to accept that the prototype they were about to test was already obsolete before it flew, because they'd committed to a better version that didn't exist yet. Every one of those decisions could have gone differently. The Navy could have stuck with the R2600 because it was available and changing engines was risky. Grumman could have declined to redesign the airframe because they had contracts to fulfill and shareholders to satisfy. The Bureau of Aeronautics could have played it safe and produced a marginal improvement over the Wildcat rather than gambling on a more powerful but more complicated aircraft. Any of those decisions would have been defensible in April 1942, when nobody knew for certain whether the redesigned F6F would actually work. But that's not what happened. What happened was that people looked at incomplete information, made educated guesses about what would work, and committed to those guesses, even though they were betting careers and lives on being right. The F6F Hellcat succeeded because the right people made the right guesses at the right time. The pilots who flew Hellcats through the Marianas, Iwo Jima, Okinawa, and the final strikes on Japan never knew about the April 1942 decision to change engines. They just knew that the F6F worked. It kept them alive. It shot down enemy aircraft. It came back to the carrier even with battle damage that should have been fatal. And that was enough. The difference between the Wright R2600 and the Pratt & Whitney R2800 was 400 horsepower and about 300 pounds. On paper, it was an incremental change. In practice, it was the difference between an aircraft that could barely match the Zero's performance and an aircraft that dominated it. That's what makes the Hellcat's development story significant, not because it was revolutionary, but because it demonstrates how much difference the right engineering choices make when they're applied to a fundamentally sound design. The F6F's airframe was conventional. Its armament was conventional. Its systems were conventional. What made it special was that every conventional choice was optimized for the mission it would actually fly rather than the mission planners thought it would fly. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.